So as we were saying before, rational function is a polynomial over another polynomial, and they're important. They model things that have limiting behavior, like when you take a drug, then eventually over time, you start to not be, exercise is like this too. Exercise, you can work out initially, and we call that a dose response. Like you initially the exercise does a lot for you, but after a while you're just like, it becomes easier and easier because you're getting used to it. So that's called limiting behavior. It has those, and it also has asymptotes, which we see in what we call shocks. I don't think you'll see it anytime soon, but if you're going to engineering, you will. They make these kind of different graphs. So this was the one that I showed you. This one right here was the one I showed you with the lines as being the asymptotes. Here you have horizontal asymptotes that are the at y-axis, for example, and sometimes you can have a horizontal asymptote where it's an actual value somewhere else. The end goal is, if you're given the rational function, fully graph it. The one thing I didn't show you that's in your book is they sometimes want to graph it by taking 1 over x, which they know the graph, and the other graph is kind of a shift or a scaling of 1 over x, which he's going to show you in class. That's not that hard.
Well, I kind of know how to do that already because he showed us how to do it with other stuff. So.
But the simple toy problem is 1 over x. Step 1 is to find the problem points. They're usually where the denominator is 0, but not always, like I showed you in that last problem that were, it's true, math teachers do purposely try to trick their students. Now you know. So there's x not equals 0 is, you can never let x be 0, so x equals 0 is the problem point. Once you identify that problem point, you want to select x value slightly to the right and slightly to the left of the trouble point, which is x equals 0 in this case. You could have more than one trouble point. We didn't do a problem like that. I did at the end, actually. I just didn't do it neatly. So slightly to the left of 0 is minus 0.01. Slightly to the right of 0, misspelled, is 0.01. So you get minus 100 and 100. That tells you they're very large. I should have actually chosen something like minus 0.0001. That'll give you a good reflection if it's heaven or hell. So that tells you that it's going to hell as x goes to 0 from the left, and it's going to heaven, the y is going to heaven as x goes to 0 from the right. So that's what it looks like. So you're getting pieces of the graph as you're going through these steps. So that's the piece I got. We say formally that that's the limit as x approaches 0 from the left. This is how we write it, like that. We would say that that's minus infinity. And this would be as x approaches 0 from the right. And we would say that equals, I didn't put that equals plus infinity, right? That's what we're seeing. X equals 0 is what we call a vertical asymptote. Then we want to find out what's called horizontal asymptote. What happens as x goes really large in the plus and minus direction. So you should do this numerically first with numbers, and then if possible try algebra. In this problem you can't do algebra. It's so obvious. You choose a very large negative number, which is a candidate or a proxy for minus infinity, and then you choose a large positive number, which is a proxy for plus infinity. So that's what I mean by that. And you get that. That tells you that the limit as x approaches minus infinity of 1 over x is 0, but it's approaching from below 0. So it's going underneath the y equals 0 axis. On the other hand, as x approaches plus infinity, you're coming down from on top to 0. You're approaching from the top of the x-axis. So again here, so I'm approaching the y-axis from on top. This is y equals 0. It's approaching from on top. And on this side, it's approaching from on bottom. So that's called a horizontal asymptote.
So if you do a negative x and you get a positive y, then it means that it's flipped. So like it's coming down on this side and coming like that.
Yes, whatever the numbers tell you. So if this minus sign was over here, this all would be reversed and it would be approaching the other side. Now, one thing is when you get the pieces, other pieces in place, so sometimes my students would get these numbers wrong or make a minus sign error here, and so they'll get it's going to heaven from above and then it's going to 0 from below. Well, that doesn't make sense, does it? It would have to go to heaven and then go down and then go like this. It can do that, but if it starts to look really weird. There's a picture in one of your problems where it does something funky like that. see if I found, like here, you see it was, so it can do something weird like that, but most of the time that's unlikely, and you will also see it on your TI.
Yeah.
So there's triangulate, and you'll see that's very unlikely, but sometimes I'll see that the students have something like this, and they'll say that it approaches 0 from below, and they'll be trying to figure, like they'll look at their numbers, they'll never think, well, I must have made a minus sign error in my numerical table. They'll just try to somehow force it to do. So you'll see that. So if the numerator has roots, you want to find them and plot them. Those are the y-intercepts. There's no roots here. The only way you can have roots is if the numerator has roots. In this case, the numerator is 1. Sometimes students find roots from that, but that's a bad thing. The second is if you positively want to find the x-intercepts, you can't do it here because if you set equals 0, x equals 0 is your trouble point, you're not allowed to do that. Here's a more complex problem. R of x equals x squared minus 4x minus 5 over x minus 3. You want to find the problem child, which is next door, which is Aishu, or the problem point. So x equals 3 is the problem point here because that's what makes the denominator 0. So that's your potential for a problem. And it is indeed a problem point because if I put a number to the left of 3 and a number to the right of 3, I see that to the left of 3 it's going to heaven, to the right of 3 it's going to hell. See that? To the left of 3 it's going to, so I have a little mock-up of what it looks like right around that point asymptote. That's step 2. So what happens as x goes to infinity? In this case, you can't just plug numbers in because you're just going to get it goes to infinity as x goes to infinity. There's something more complicated happening, and I did my long division incorrectly here the first time, right? Yeah. I fixed it. So long divide, this is what you get. What that tells you as this part here asymptotically, we say asymptotically, as x gets larger and larger, this damps out to 0. That's because big bottoms go to 0. They always do. Big bottom, this has a 2 divided, think of 2 divided by 1,000,000. It's going to be something close to 0. So this term we say damps out as x goes to infinity. And so as x goes to infinity, the function will behave more and more like x plus 1. Then it will, like this piece will become negligible as x gets large and large. That's the point. Okay, so we have different ways of saying it. We could say wiggle, x plus 1 minus 2 over this wiggle, little tilde, x plus 1, asymptotically, that we actually write it out. So I put that up there. So what that means is, as x goes to infinity, here's y equals x minus 1, the line. It will tend towards that line as x goes to plus and minus infinity. Okay? And above and below, again, you should technically put in numbers and see does it approach this from above or below, but again you already have the shape of the asymptote. How could it possibly go to the below from here? How could it approach? It would look so awkward, right, if you put that line in.
So well, the one function can't fail the horizontal line test then, so like it could never be,
no,
it could never go like this and then go.
It's not, it's a function, right? You
Yeah.
could have something weird. They have other kinds of functions called.
Well, like none of these go.
You could have something called a hyperbola, where that could happen, but this is not. That's not this case. These are not like circles. Those kind of things are when you have y squared is equal to, right? So.
But you never see like the one, like if say you had this, you would never see it come back up like that.
No.
Okay, so yeah, so then it could never be like this.
Right, that's right. But sometimes people make it wrong and they're trying to force it to do whatever they're seeing. But that's why I don't need to do any more checks, because it cannot go down like this and then underneath why it has to approach this. So there's no way for it to go except to flatten out from top.
So basically, if you know that this angle is greater than 90 degrees, you can assume that it's going to go like
right. You could also refine your graph more. In this case, you can find the y-intercepts because it does have zeros on the top. With it, in my class, we call these fake functions because these kind of functions never happen in reality. I have never been able to had something that actually factors in real life. Things in real life are a lot more messy than that. But what that tells you is you have 2 zeros, and I had drawn this so badly the first time. Now I had to refine my graph so that it actually goes through -1, and then it eventually tends toward this red line. And the other side was drawn a little bit better, not much, but it goes through 5 and before it goes down to hell, and then it flattens out at x minus 1, and that's a more refined graph. You could also find the x-intercepts, which is when you plug in x equals 0, you get 5/3. That means, oh, that's the y-intercept. I got these two mixed up. X-intercept, y-intercept, other way around, okay? So what happens when y equals 0 and what happens when x equals 0? So then you have this 5/3 here, and some teachers like to have, like I usually make my students do that because most of them have the TI 83 and the 84 plus, 86 plus. They have those, but they don't know how to really look at the coordinates. So I like to force them to actually use their calculator a little bit more and look at these coordinates and label them. So
I'm wondering if I can find when it intersects the y-axis on here, because then I can just.
You can use the trace button, but it will tell you. You can put x equals 0, y equals 0. You can just look at your table and it'll just tell you. So one last problem is a trick problem. So most students will internalize for some reason that if the denominator is 0, it's a vertical asymptote, which is not true. And so I give these kind of problems where there is 2 roots in the bottom. In this case, there's 2 roots in the bottom. It turns out there's plus and minus 1. If you do difference of squares, x minus 1, x plus 1, you'll actually find 2 roots here. And they'll automatically say that there's 2 vertical asymptotes. This is in fact untrue. And you can see it from the numbers. If you actually plug in numbers, you don't see a heaven or hell here. Sometimes they just keep going and they say this is hell and this is heaven. It's not. This number is close to 0. Right? So it's not even close. This is not lying to you. The numbers are not lying to you. It's telling you that x equals 1 is not a vertical asymptote. In fact, only x equals minus 1 turns out to be a vertical asymptote.
Well, because you can simplify. If you couldn't simplify the top one,
it's what we call a removable discontinuity, because we can remove that discontinuity. However, this is something that consistently I've seen, like 3/4 of the class will say that there's 2 asymptotes plus and minus 1 if they factored the bottom right in the first place.
If you can't remove it though, then there would be 2 asymptotes, right? So like if the top wasn't, if it was like x squared plus 2x plus 1, or something like that.
Right.
It's not that one, but like x
plus 3.
Plus, yeah.
Then there would be 2.
Then there'd be 2.
Mm-hmm.
Okay.
So that's not an asymptote over here at x equals 1, and this is. And the numbers are telling you the truth. It's telling you that business. So the reason is this is a removable discontinuity. You can remove the x equals 1 as being a problem point. It doesn't mean that these two are equal. It means that as long as x is not equal to 1, I'm allowed to do this calculation. And in fact, the way you're supposed to draw it is with a hole at x equals 1, because you were never allowed to plug x equals 1 in the first place. So it's not an asymptote, but there's definitely a hole there. It's just a non-existent point. It's a discontinuity of a different type. This is a discontinuity also. You pick up your pencil when you draw this.
Yeah.
But there's a hole there. We call this a removable discontinuity, because you can remove it from consideration, but it's still there. It's a hole. It's a gap. So that's not an asymptote. This limit here, as x goes to infinity, you could put in x equals, so the horizontal asymptotes in this case turn out to be 1. It's approaching 1 from below and approaching 1 from above from the left as x goes to plus and minus infinity. And I can tell that, another way to tell that, instead of just plugging in 10,000 and minus 10,000, you could actually do a trick called divide by the highest power. The highest power in here is x. Divide every term through by x. You have not changed the function at all. You're really multiplying by 1.
Yeah.
And this reduces to 1 minus 1 over x, 1 plus 1 over x, and big bottoms go to? Big bottoms, 0. So you get 1. So that from above or below, this thing tends to 1. So that means that you have horizontal, it flattens out at 1. And you can even tell where it flattens. It has to go from above to 1 and below on this side to 1, because again, it would be weird, right? You'd have to make it go above 1 and then back down. That's not going to happen.
Yeah.
So that's it. You're set?
Yeah.